Yeah. Okay, so thanks everyone for coming to our final climactic talk of the year. So we're very happy to have Djordje Radicevic from Perimeter, who's going to talk about his work on defining entanglement entropy with Jennifer Lin. So Djordje, thank you very much, and take it away.
Okay, thanks. I hope everyone can hear me. If you can't, just shout or do something and we'll pause to fix that. This is my first time doing a virtual seminar from anywhere, so if I make mistakes, please excuse me. And in addition, I have just yesterday gotten off a 15-hour plane ride, so I might be slightly dazed anyway. So yeah, I have plenty of excuses if things go wrong, just in case. Excellent, and thank you for inviting me, for letting me talk. I'm going to talk about something that I've been thinking about for quite a few years now. It's not by now I've gotten to the point where I feel like it's a subject that at least fundamentally is pretty well understood, but there are many calculations available. They're difficult calculations, and it's not necessarily easy to do them, but at least I can offer some insight into the status of the subject, etc. And the subject is just entanglement entropy at its most basic. So I'm going to talk about some subtleties that one has to deal with when trying to define it in regularized quantum field theory. So even if you don't worry about divergences, you still have many issues and choices that people did not appreciate until very recently. So I'm going to talk about that. I'm going to give some examples, and yeah, feel free to interrupt and ask questions or complain and so on. And I will try to address as much as possible. Okay, so as Rose said, this talk will be based on an article that I wrote with Jennifer Lin, where we sort of focus on systematizing this knowledge, and it's up on the archive, and so you can check it out if you want most of this talk spelled out. Okay, so to begin with, let me just start with talking about what entanglement entropy is, even though, for this audience, I'm sure it's already quite well known. So the idea is that entanglement entropy gives us some quantitative way of probing the structure of entanglement in a quantum field theory, or in any quantum theory in which we have some notion of a spatial manifold or lattice. So the idea is to calculate a kind of measure of entanglement that is associated to a particular region of space, and to think of that as a way of quantifying the entanglement between that region and the rest of the space. Entanglement entropy is calculated separately for each state. So it says within a state, what is the entanglement of some region with the rest of the world? And there exists a very conventional definition of entanglement entropy that you can see here. Oh, by the way, can you see my pointer? Is that okay if I use my mouse arrow?
Yeah, that's good.
Okay, so I can do things like this. Okay, so the idea is that you start from a state given by a density matrix rho. It need not be pure, but in most applications, one takes just the density matrix corresponding to the ground state of your theory. And you pick a region, and that I will call V. And the conventional definition is that you define this object called a reduced density matrix by tracing out all the degrees of freedom that live outside of V. As I wrote here, I denote them by V bar. And then you get some other operator, which is also a density matrix. And you can calculate its von Neumann entropy that I denote by SV, by this formula here. And this gives you some number, and that number is a very interesting thing that one can compute about in different theories, and it knows a lot about the ground state or the state of the theory in question. one thing about this kind of number is that because we are talking about, we're associating some number to a sharply cut out region, this object probes very high energies, arbitrarily high energies in a continuum field theory. So it will always generically diverge, and it will always need to be regularized in some way. And the simplest and definitely my favorite way of doing this is by just putting the theory on a lattice. Pretty much most theories we care about, with some important caveats, can be put on the lattice. We may not know how to tune to a particular conformal point, but at least we know how to put the right amount of matter fields and some kind of potential. And in that context, you can ask, okay, so given such a regulated theory, what can we compute? But then it turns out that there are certain issues that remain, even if you don't worry about the divergences in this entanglement entropy calculation. The first and foremost of these issues is what happens if the Hilbert space does not factorize, which is the case that happens fairly often in many theories of interest, in particular engaged theories, or in any theories in which there are constraints in general. Then you cannot just nicely trace out degrees of freedom living in some subregion, because there's a constraint which relates in the interior and the exterior. So you need to, so this definition, as I wrote, does not stand. And then there are other issues that I've thought about in certain, to different degrees. For instance, even in the simplest settings, it's a non-trivial question to understand how entanglement entropy maps under a duality. You would expect it should be equal, but it actually turns out that getting it to be equal is a sort of subtle thing. If you just naively calculated it in the way that I just described, you would not get that it is equal under dualities. So I will touch upon this. This is not going to be the main subject of my talk, but I will touch upon that later. And another issue, which is perhaps less serious, but still fundamentally kind of needed some clarification, is the status of entanglement entropy in fermionic theories. So these are theories which are still local, but of course, operators that are very far away can still fail to commute. So there's some, because they're fermionic. So there are ordering ambiguities when you start defining a Hilbert space for such operators. So again, tracing out degrees of freedom in part of from part of the Hilbert space is actually has some subtleties too. So I will talk about how one can deal with this. Essentially, the answer is you deal with this by dualizing, which you can do always. And that's going to tie up these second 2 points. So the point is that I will give you many examples, and I will show you how these issues that I've listed here can be addressed in a very general manner. Okay. So I will just give you the spoiler immediately. Essentially, the point is that you need to talk about a more powerful definition of entanglement entropy. The one that I just gave you is not going to be valid. And the nicest way to think about this, and probably the correct way of thinking about it, is to think about assigning an entropy not to just a region, but to assigning an entropy to some operator algebra that is supported in a given region. So now one has to talk about operator algebras and understand what it means to have an entropy associated to them and in a given state. And so to that end, recall that algebras are just vector spaces which are equipped with a multiplication that keeps you in the space. So a nice example are complex matrices of a given size that form the algebra of all dividing complex matrices. And basically, for all the operators that I'm going to talk about today, you can just think of them as large, very, very large matrices. And since I'm regulating everything, as I said from the start, I should not, this is a valid thing to do. And now, the next question is how does one define a reduced density matrix that is associated to an algebra? And when I say an algebra of operators, I essentially mean a set of things, a set of operations one can do on a given state. So let's say I give you a region V, and then I say, okay, so here are some allowed operators that live in the region V. These are the manipulations I'm allowed to do on my quantum system. And I demand that this set of operations be something that I call a unital star algebra, meaning that it's unital, meaning that there is an identity element. So I always have the option of just not doing anything to the state. And the star property just means that if an operator is in the algebra, then its conjugate, then its Hermitian conjugate is also in the algebra. If this is not true, if the algebra is not star, it turns out that I can always just restrict myself to a smaller subalgebra, which is star, and repeat the procedure. So this is a technical assumption which I will just take from the outset. So say I have a set of operators that satisfy these mild criteria, and they're all supported on some region V. Then I can define, given a state rho, a density matrix rho, I can define a reduced density matrix, which is one of these operators, which is simply an operator in this algebra AV. And it is a unique operator that satisfies this equality here, that reproduces the expectation values of all the operators in AV by doing this, by tracing it into the required operator. So this is a fairly abstract equation as it stands, but it turns out that in many cases of interest, and in all the cases that I will talk about, it is exactly solvable. And I can actually show you what the exact expression is for rho v in terms of a set of operator expectation values. So, excuse me. So there is a way to just abstractly be given a set of operators and to uniquely deduce an appropriate reduced density matrix. And then once you have that, that's again some operators, that's again some matrix for which you can calculate the von Neumann entropy in the usual way as before. So the important thing is to identify which operators you're working with, given that are supported within a region. And then the non-trivial thing is really to calculate the density matrix that is associated to that particular set of operators. That is the more abstract and much more powerful way to deal with this issue. And you notice that I never assumed that the Hilbert space factorizes or not.
Djordje?
Yes.
Is it obvious that this restriction of the density matrix PV has to be unique? Because naively going the other way, it's not, right? If you start with a subset, I can purify it in many different ways. It's like, is it obvious from just this expression, or?
You mean that there's a
Yeah, that it's a unique solution.
It's going to be obvious when I write down the explicit form. Basically, as I said, you can solve this equation, and it turns out that it has only one solution.
I see. Okay.
That assumes that all the operators I work with are, or at least the basis operators in this algebra, are invertible. There are some technical assumptions which make it very clear. I did not plan to go into this. So basically, the point is, I can do this not for all operators in the algebra, but for a nicely chosen basis for that algebra. And once I do it for that nicely chosen basis, I can actually prove that it's unique. It's not obvious as it stands, I agree, but you can do better if you want to.
Okay, thanks.
Okay. Okay. So, and as I said, so here's the summary of the definition as I propose it. And I mean, of course, it's not, I did not come up with this. And this was the kind of approach that was done to quantum information theorists for more than 10 years for sure, probably 20 or probably even more. So just applying it to, lattice gauge theories and in general conformal, in general quantum field theories is something that has not really taken off until recently. But the philosophy is quite old and well established. And so, okay, so now we reduce the issue to essentially understanding the choice of algebra that has to be made given a region V. So it turns out that there is not a unique way to choose an algebra of operators that are associated to a given region. And the fact that these choices exist is important for the duality story, among other things. And not only is it important just as curiosity, for gauge theories it's extremely important because it turns out that phenomena which you might not think are natural in scalar theory come to the fore in a gauge theory when you talk about different choices of these operators, of these algebras. So I will give examples of this. That's the point of the talk. So right now I'm just giving an abstract overview, so please bear with me. And the second thing that one has to ask is, which representation are you taking the trace in here? When you talk about the von Neumann entropy, so far abstractly, I've just given you some algebra, and in principle, the information on the trace is extra data that you can choose to somehow include, and this turns out to be important because for non-abelian theories or for subtle theories like that, where you actually can get different representations, and they will contribute differently to the entanglement entropy. You can convince yourself, by just looking at this trace rho log rho that this is something that will actually change if you are using a reducible as opposed to an irreducible representation. So this is something that will need to be kept in mind, and the effects of this will be important later on. And let me just emphasize that I already mentioned that the choice of algebra that you associate to a given region is important. It gives you different choices, give you different answers for the entanglement entropy, and in particular, if you have some rule which assigns an algebra of operators to a given region, in essence, very broadly, you can think of this rule as assigning boundary conditions at the edge of the entangling region. If you have some rule like that, it turns out that dualizing and insisting that the duality of QFT preserve the entanglement entropy, that dualizing then has to be done by covariantly changing this rule for picking operator algebras in a region. So it's a very interesting story that I will touch upon later because I will need it a little bit later on. And I should say that depending on your philosophical outlook, you may say that because you have these choices, which sound like some random UV choices that you're making, it seems like entanglement entropy might not even be meaningful in a QFT. And in a seminal paper where they talked about gauge theories, Cassini, Huerta, and Rosabal actually speculated that maybe the only thing that makes sense is mutual information. I'm not that pessimistic. I think that entanglement entropy is a concept which, if you keep track of the regularization, is well defined. I think that there's more to entanglement entropy than just the universal terms, and the fact that the fact that it's still diagnoses interesting phase transitions and so on, has interesting bulk duals and so on, I think justifies thinking about it on its own. You don't have to go to more complicated entanglement measures just yet. Many things can be made meaningful. Okay, so let me give you the outline for the talk, for however much of the talk is left. So I will give you explicit examples in which in which one calculates different using different choices of operator algebras in a subregion in different theories. And the theories I will work with will be nice regularized theories. As an example of scalar theories, I will use spin systems. I will also look at fermion systems, and I will look at gauge theories, lattice gauge theories, both abelian and non-abelian. And the point is that the same methodology will apply to all of them. It's a very unified approach. And in particular, not only does the same methodology apply to them, but also the same subtleties will arise in all of them. So when people say that, entanglement entropy in gauge theories is ambiguous or dependent on certain choices, that's actually true for all entropies in all theories. With the possible exception in being these interesting condensed matter theories called symmetry protected topological phases, which seem to be special theories in which you sort of have some protected kinds of edge modes. You can't get rid of them by a choice without changing the size of your region. Chern-Simons will be like that too. So there's a special case of interestingly anomalous theories where it turns out that there's only one choice that can be made given a region of a specific size. But that's sort of a special case. Like in all your vanilla scalar theories or super Yang-Mills theories, etc., you have choices that you need to make, or you need to be aware of the default choices that, let's say, Rita Kanagi makes. Okay. The point of this talk will be precisely that choosing different algebras at the level of doing a path integral, which is the sort of preferred method for calculating entanglement entropy, is that these different choices correspond to different types of boundary conditions, and as I will explain in detail. So, roughly speaking, the maximal algebra in a nice scalar theory will correspond to open boundary conditions on the entanglement edge, and smaller algebras will correspond to Dirichlet or Neumann kinds of boundary conditions, where you constrain the kinds of fields that you can have in a specific way inside or on the boundary of your region. So this is a main point of this talk. Now, I already mentioned that there is this idea of a maximal algebra. So I kind of just briefly mentioned it just now, but let me now elaborate on this a bit more. The point is that if you're given a region and you're given some set of physical operators in your theory, then you can look at the maximal possible set of physical operators in your given region. That's a unique entity, and they form this thing which I will call the maximal algebra on your subregion. And it turns out.
I'm confused when you say it's unique, because naively, if I do this the story where I put it on a lattice and then I have to cut the links of my lattice, don't I get all these edge modes that are now I have to decide whether to count them inside the interior algebra or not?
Good question. No, that's being a little bit too imprecise. So I will never talk about cutting links. I will only talk about when I say subregion, it's going to be some subregion which includes some set of links. So I will not talk about the notion of a subregion where a link has been cut. That's not something that, in simplicial geometry, that's not something that I can think of existing. So I will specify a region by specifying a set of points, plaquettes, links on a lattice, and that's it. And then I look at all the possible operators which are supported on these sites or links, etc.
So for suitably defined subregions or subregions defined in this abstract framework, there is a well-defined maximal algebra, which is in this sense unique. It's only
That's right. So as long as I'm able to tell a mathematician what I mean by a region on a given lattice or on a given complex or something, then everything else I say will be unique. Yeah.
And this is even
there will be a unique maximal algebra.
Gauge theories, or is that related?
Sorry?
Is that even like this works as well for like gauge theories?
Yeah, exactly. Yeah, because gauge theories just have operators that live on links. So I said that my region will contain some set of links. There's not going to be a sort of we're not talking about some Schrödinger regions where, like, you know, you may or may not have a link in it. Basically, if I give you a region, you know which links are in it. Okay. There's no doubt about that. And then I can just look at what the possible gauge-invariant operators are that are supported just on those links.
Okay. Okay. Very good.
So, yeah. So the point that I wanted to make is that the notion of the maximal algebra is important because it ends up giving you the results that are precisely what people have been calculating in other ways. So in free theories, you can actually check that it's always the maximal algebra that matches the various conformal and trace anomalies that are also being reproduced by holography. So that's sort of the guiding principle that pretty much every method that has been used to calculate entanglement entropy in the continuum directly, so either holography or fancy, you know, twist operator methods, etc. These operators have sort of on the nose been using the maximal algebra, and so one can then ask, how does one modify these methods to talk about non-maximal algebras and different boundary conditions? I will not necessarily talk much about that, but those are the obvious open questions here. And yeah, and in particular, Chern-Simons theory will give us an interesting, very non-trivial example of the importance of these regions, of thinking in this way, because there, in order to reproduce the known topological entanglement entropy, you need to realize you need to trace over all degrees of freedom. So you need to trace over a reducible representation of your gauge group, which turns out to be a very unusual situation. Well, you would it seems that it is a unusual, unnatural situation, but I think that this is a sort of smoking gun which shows that this is what you should be doing anyway in all theories. So I will come back to this later. So the point being that sometimes even gauge non-invariant notions need to be taken care of, need to be addressed in some way. This is a very deep thing. Like I'm not professing full understanding of this, but I will give you examples where it turns out that gauge degrees of freedom are important for getting the right continuum descriptions. So. But let me go back to more elementary things. So I want to give you examples of what I actually mean by algebras in these systems. So I will talk about. I will organize my thinking about algebras, because they're vector spaces. I can think of their basis elements, but I can do even better. I can think of generators of an algebra, and I'm not talking about Lie algebras here. I'm talking about just abstract algebras. And their generators are operators whose all products give you a basis for this algebra as a vector space. So let me jump to this example of spin systems. So here, normally in a spin system you have 2x2 Pauli matrices as your quantum operators at each site, and so you kind of have 4 possible operators corresponding to the 3 Pauli matrices in the identity at each site. But the point is that you can generate this set of 4 operators by just taking different products of 2 operators of 2 Pauli matrices, X and Z, because both of them square to the identity, and X times Z gives you the Y matrix. So I just need to specify I just need to list X and Z matrices as generators of my algebra on each site, and then we take them all together, consider all possible products, and then linear combinations of products. And that literally gives me the set of all possible operators in a spin chain. So that's the sort of most economical way of thinking about algebras, in terms of to think in terms of their generators. The same thing can be done with fermions. Here you can just think about having a, let's say in the spinless case, you don't think about spinors or something. In the completely nice spinless case where you have just complex fermions, you can just think of two generating operators per site, the creation and annihilation operator for a fermion at a given site. If you have a more interesting theory, like a scalar theory, there you need to specify. There you have again two generators, which correspond to your momentum and position on each of the scalar at each point, and their different products will eventually give you the full algebra of the scalar. You can of course discretize these kinds of things and think of them as sort of a discrete compact scalar, like a zk compact scalar, or a clock model. And I will talk a little bit about that too, because it's very useful to think instead of thinking of a U1, like a scalar on a circle, it's often nice to think about a scalar that is really on a clock, on a discrete circle. Good. And the point is that if I just specify all of these possible generators, then on a given region, then these will generate the maximal possible algebra on that region. In particular, this will give me some notion of all possible d by d matrices, where d is the appropriate dimension of the Hilbert space. But many times we actually care about a smaller set of operators. So I will not choose algebras that are generated by these lists of operators that I just gave, but I will choose some smaller algebras that are generated by different operators. So if I have a fermion theory, I very often only care about fermion bilinears. So either psi-Dagger of the form psi-Dagger psi, or including or excluding operators of the form psi-psi, etc. The point is that these operators are all bosonic. If they're far away from each other, they will commute with each other, and then they're much nicer in some ways. But the point is that this is not a maximal algebra that you can associate to a given region. If you just look at the algebra of fermion bilinears in that region, there are fermion operators which are not including. Similarly, in a gauge theory, you have degrees of freedom living on links, and you only swear to look at gauge-invariant operators. So that's a much bigger restriction than just going to bilinears. You're allowing yourself to look at all possible momentum operators, like this thing that I call d over dA. Very often this is called the electric field. And you're allowed to look at all the possible magnetic operators, which I denote by e to the I delta A. Delta A is just, you can think of it as the lattice version of the curl. So this is just the analog of a Wilson loop, e to the IW, along a small plaquette of the lattice, which I will denote by F. So these are just some technical conventions. It's going to be easy to just go back and check the technical conventions. But the point is that sometimes we actually care about an algebra of operators that's generated by some smaller set of operators, either gauge-invariant operators or fermion bilinears or something like that. And when this happens, typically a non-maximal algebra will have a center. It will have operators which commute with all the other operators. So, for instance, when you have an algebra that is generated just by fermion bilinears, then there exists a Z2 operator, the fermion parity, which is a symmetry, which commutes with all possible fermion bilinears, and it's defined like this. If you have an abelian gauge theory, then you will have you will have a central element on each site. We call it the Gauss operator, and get it just by multiplying all the electric field operators that emanate from a given site. So things like that are important to keep track of, because because they simplify the analysis greatly, because you can diagonalize all the central generators simultaneously, and then you're really talking about block diagonal matrices all the way through. in particular, I will always work when I work with non-maximal algebras, or theories which do not have all the possible operators that you can imagine. Then I will always assume that my starting state is an eigenstate of these central operators. So it's a pure state which does not mix these different superselection sectors that are given by different eigenvalues of the central operators. So this will be a simplifying assumption, essentially, or an assumption that I'm only working with pure states. Good. So let me elaborate a bit more on the importance of centers. I kind of mentioned that when you have a center, you can sort of block diagonalize everything. And these blocks are things that I will call superselection sectors. In particular, I said that all operators will be block diagonal in case of a center in your algebra. And indeed, if you have some subalgebra A of V on a region V, and that algebra has a center, then the appropriate density matrix must also be block diagonalizable. And as I said, then each block of this algebra, each block of this matrix will correspond to one particular eigenstate of the central generators. And essentially, you can think of each block, each superselection sector, as being a sort of quantum, as describing a quantum state with a specified type, a specified boundary condition of a particular type. So some states, so the states that live in each superselection sector, the fields there are sort of pegged wherever there is a central generator to have a specific value. So it's like imposing some boundary, some constraint, which may or may not be on a boundary in each sector. And so the bottom line of this of these words is that if you pick a subalgebra which has a center, then your reduced density matrix will necessarily be of block diagonal form, and these blocks will just be some pure states which are mixed together in some particular way, and each block can be understood as a pure state with specified boundary conditions or some specified constraints on your region. This is the point that I want to make. This is the main dictionary between central operators or choices of algebras and boundary conditions. So let me give you a clear example. So let's consider a spin chain. So here's a spin chain. Here are my spins that are labeled by these dots. And by X and Z, I label all the operators that I will work with in my algebra. So this is a region. This is a part of the spin chain. And if I choose to have all possible generators, all possible X's and Z's that can be placed in this region, and this will correspond to just a single block density matrix. There will not be any smaller superselection sectors. So this will correspond to just having open boundary conditions. You do not specify any type of boundary condition. You just allow your fields inside your region to be whatever. That's the standard thing that one does in a matrix theory. But now imagine removing one generator from your from the set of generators for your algebra. So now let's say you're not allowed to measure the operator Z at the edge of your region. For whatever reason, you're not allowed to do that. And then the resulting algebra will have a center. The center will be generated by the conjugate operator at the edge, which in this case is X. You see, there's no other operator which fails to commute with X now that Z is out of the way. Y is also not there because you need Z to build the Y in the way that I'm talking about. So there are no other operators on this edge site. And because of that, all states that are expressible using an algebra generated by these operators will be block diagonal, and within each block, they will have a specified eigenvalue of this operator x. So there will only be two super selection sectors in this case, because this operator x has two possible eigenvalues, plus and minus 1. So what you're doing here is you're essentially saying that you're, by choosing this particular algebra, your reduced density matrix has to be a mixture of two states, and one state with a definite, and both states will have a definite value of the spin x component at one edge. So basically, you're saying that your general states in this algebra have Dirichlet boundary conditions at this red edge, and on the other edge they have open boundary conditions. I'm just allowing anything to happen on this other side. I can do fancier things. I can remove two individual operators, but put a generator which contains their product. So basically, I'm saying that I can consider a situation in which I will always have only products of these two operators, not them individually. This also generates a viable algebra, and this corresponds to specifying Neumann boundary conditions. Because if I only have the generator XX, then you can quickly realize that the appropriate product of the two Z's is now going to be a central element. It will just commute with everything. It will commute with the two X's, and it will commute with all the other stuff at all the other points. So this is like specifying this is like specifying the relative position of the two spins at the edge. This is like specifying the derivative of the spin field at the edge of your region. So that's why I call this the Neumann boundary conditions. And of course, now you can go crazy. Now you can mix different boundary conditions on different edges of your region, etc. But the point is that, and in particular, you can then choose algebras which have missing operators even in the interior. But I will not do this in this talk. So this is in general the kind of correspondence that I will want to have in mind. And so now let me go back to talking about the subtle parts of this kind of thinking about algebras. So if you have a gauge theory, let me start with that. Then the maximal algebra will always have a center. That's a non-trivial fact of life. That's sort of the thing that was first realized, sort of before we even realized how to think about gauge theories in a nice operational way like this. And basically, it's basically you can check that there exist gauge-invariant operators which are going to be central, and these gauge-invariant operators are precisely the total electric fields that go out of your region, that live on the boundary of your region. So basically, a reduced density matrix for in case of a maximal gauge-invariant algebra in a region will always be block diagonal. You can't escape from that if you're working with a maximal algebra, and these blocks will be labeled by different possible values of the electric field going out of your region. These possible values of boundary conditions are things that people call edge modes. And I call them K here at the bottom of the slide. X parallel is just the sort of direction along the entanglement edge. So in general, I will think of having arbitrary some abstract boundary conditions that I will label by K. And the entire point is that my reduced density matrix does not have just one particular kind of Dirichlet boundary condition. It's not like I'm just putting the field to be equal to zero, some field to be equal to zero. The point is that in the most generic case, which will indeed happen often, your reduced density matrix will mix states which have different boundary conditions of the same class. So in the previous example of the spin theory, I'm mixing states which have an edge spin equal to 1 and an edge spin equal to -1. So these are both Dirichlet conditions, but they're Dirichlet conditions with different boundary choices. And these different choices of boundary conditions within the same class are what people call edge modes. And then there are pictures of getting them by cutting links, which I do not necessarily subscribe to, because the way I presented it here is much more precise, at least. So here we go. So and as I said already, like when you talk about gauge theories, you kind of want to imagine having degrees of freedom on all links. So even the ones that are not gauge invariant, and then you can just consider a set of gauge invariant operators that live on these links, and that will sort of give you density matrices which correspond to only gauge invariant states. So you do not have to do any fancy projection on the Hilbert space to get a gauge invariant space. All you need to do, and in the context of Chern-Simons theory, the correct thing to do is to just look at all possible degrees of freedom, and to think of possibly a smaller subset of operators that will impose gauge invariance. Something is beeping here. What does this mean?
Maybe somebody else will turn on.
Okay. Should I continue?
Yeah, just please, yeah.
Okay. If there are any questions, yeah, like I guess Ro knows how this software works, so he can tell me, and I'll try to take the question. Okay. So let me now let me go back to this other example that I gave about fermion bilinears. So this is a simple example because there's not that many central elements going around. You really only have one big central element, not one per site or something like that. And this one big central element is just the fermion parity of your given region. That's fine. Now we can also ask what happens when, like, you know, when given a fermion theory, how does one deal with the fact that the Hilbert space is graded, the fact that there are some ordering ambiguities in the definition of the Hilbert space, and therefore in the definition of the trace over rho log rho. And the way to do this is actually to dualize. The point is that every time you have a fermion theory, if you just look at its algebra of bilinears, in any dimension, it is dualizable to a Z2 system, to a bosonic system of Z2 degrees of freedom. In 1+1, this is the standard Jordan-Wigner transformation. In higher dimensions, it's more complicated, but nevertheless, there exists a mapping between bosonic degrees of freedom and fermion bilinears. I will not talk about spin structures here, but this is an entirely orthogonal set of papers, essentially. But the point is that I can reduce any discussion of fermions to a discussion of non-maximal algebras of bosons, or rather, particularly of spin systems. So that's the abstract way of telling you not to worry about fermions at all, because this can be understood. Yeah, let me continue.
Can you elaborate a bit more? So do you treat this as a duality, as an example of a duality, or?
Yeah, exactly. Yeah. So the entire point is that it's an exact duality, meaning that every operator in the every fermion bilinear, no matter how far away the two fermions are, no matter anything, any fermion bilinear can be written as some appropriate bosonic operator. It may be a spin operator, or it may be an operator in a Z2 gauge theory or something, or in some higher form gauge theory, depending on the dimension. But yeah, so I'm just saying that at an abstract level, there is a completely exact mapping between the two. And at the level, and the algebra does not know whether it's bosonic or fermionic. You know, I just have an algebra of bilinears, and I can think of them as coming from some bosonic system. And yeah, so in that sense, I can think of having dualized my fermion system into a boson system, and then kept taking the trace in some well-defined way, where I don't have to worry about possible minus signs while taking this trace, etc. That's the point that I wanted to make.
Djordje, just for timing purposes, we've got maybe a little over 10 minutes left. If you're,
That's fine. Okay. I mean, like the main thrust is already. I've already given the main thrust, and like in fact, I said this current slide I already have mentioned. So the entire point is that in free theories, especially in like interesting complicated free theories like a four-dimensional Maxwell theory, we can actually compute the contribution to the universal piece, let's say, using different choices of algebras. So I can choose the maximal algebra in a given region, or I can choose a smaller one that corresponds to different kinds of boundary conditions of fixing, let's say, the magnetic field in my given subregion. These things can be calculated and have been calculated in some of these papers that I've listed here. And the point is that we know that predictions of conformal field theory, for predictions that the universal part of the entanglement entropy contains information trace anomaly, precisely matches the statement, the calculations made for the maximal possible algebra. And therefore the conjecture that I will make is that in general, even in n equals 4, or in a strongly coupled CFT, which you don't necessarily know how to tune to on the lattice, this is still true. And I have some path integral based arguments which I may touch upon in the next 2 slides. Again, this is something I essentially already mentioned again, so I was getting ahead of myself. So the point is that the point that I want to emphasize here is that as long as you work with gauge-invariant states, you do not need to worry about. As long as you work with gauge-invariant algebras of operators, you will be getting gauge-invariant states, and in particular, it may happen that in a certain state, some operators will have 0 expectation values, and you can sort of reduce the entanglement, reduce the algebra without ever noticing this, without ever noticing that you're not using the full set of operators. In a gauge theory, for instance, we know that there is no gauge variant operator with a non-zero expectation value. This is Elitzur's theorem. And therefore, we can just think of having even gauge variant operators in a gauge theory. But as long as we work with a gauge invariant state, we will not even detect a difference. This is why I say that in a gauge invariant state, electric boundary conditions are the same as open boundary conditions. So that's sort of inverting the logic that I was having until now. Until now, I said you only need to work with gauge invariant operators, and gauge invariant states will follow. Alternatively, you can only work with gauge invariant states, starting states, and then you will automatically generate electric boundary conditions. This is a side comment that sort of follows from the general story, it's going to be, and it sort of serves to say why these electric boundary conditions, when you put electric fields with definite values at the edges of your entanglement region, why this in a gauge theory corresponds to the right trace anomaly in the entanglement entropy. I can elaborate on this later, but for now, I just want to finish with talking about a path integral perspective on all of this. So I will not go into details of what replica trick path integrals are. This is a well-trodden path. But the point is that we can compute these reduced density matrix elements by doing certain path integrals. And the way I've written it here, so here's the origin between these 2 red points. And the matrix element of your reduced density matrix will will be defined on the upper and lower part of this region. At times tau goes to 0 plus and 0 minus in the usual way. And the point is that if I'm working with a situation where I have where I have central elements of the algebra in my given region, then if I label these the eigenvalues of these central elements by k, this labels these superselection sectors, as I mentioned earlier. Then from a path integral point of view, I will be summing over all states like this with fixed values k at all value at both t equals 0 plus and 0 minus. So there's no dichotomy here and here. Both because this matrix row in this particular superselection sector has to match fields with the same kind of boundary condition on the two sides. So in my path integral, I will be summing over all fields with these particular boundary conditions, phi k and phi tilde k, at all interior points of my region. And on the boundaries of the region, I'll be introducing just fixed boundary conditions labeled by k. This is how the situation will work in general. So this is where the boundary conditions get put in when you do a path integral in any kind of theory, not just the gauge theory. As long as you have an algebra with centers, you will have some boundary conditions of this type in your path integral. And you can think of these red regions as sort of your entanglement edges being slightly smeared, being regulated. That's a nice point of view that people have been making in conformal field theory for a while. So this is completely equivalent. This is just giving you a lattice realization of this, and then the appropriate entanglement entropy will be given by the usual replica trick. So we perform a path integral with these kinds of boundary conditions, except we also replicate the surface this little n number of times, and then analytically continue to get the entanglement entropy. So the point is that you will need to sum over all boundary conditions, and for every given boundary condition, you will do a path integral on the replicated geometry, and that will give you the total density matrix. Sorry, well, that will give you the total partition function, which you can then differentiate to get the entropy. The fact that I'm working with open boundary conditions means that there's no extra weighting here or anything like that. I'm just summing over all the possible boundary conditions in a sort of uniform way.
So can we think about this some sort of an ensemble sum with probability being the same for every method?
Yeah. So consider a spin chain. Let's say that this dotted line, this line here that I've drawn, is just where your spin chain is, and your subregion lies between these 2 points, these 2 red points, and so now, and let's say you're picking a non-maximal algebra in that region that corresponds to Dirichlet boundary conditions. I gave you an example earlier. So you remove some operators from the edges, so that now in your field theory your reduced density matrix only contains mixtures of states with definite, let's say, positions of spins at the very edge. So this sum here will have 4 terms. It will correspond to up on the boundary, up down on the boundary, down down, etc. Yeah. So for each of these possible boundary conditions, you will have to do a separate path integral, and just sum them all together without any extra weighting. And then that's going to be your full partition function of this replicated geometry with these non-trivial boundary conditions inserted.
And what is the weighting?
What is the weighting? Yeah, as I said, like basically, there's no special weighting. You just want to make sure that all these that in each subsector. I mean, the only weight. Sorry, the only condition on this is that the total this total thing is normalized. So if you were to compute a trace, if you were to trace over all of the possible boundary conditions, this has to go to 1.
No, I understand, but what was it considered before to add like some non-trivial weights to different configurations? So like say 1/2 to up, 1/4 to up down, 1/4 to down up, and 0 to down down. Like what happened to them?
Essentially, no. Essentially, as far as I know, this has not been considered. Maybe for spin chains in some particular special cases it has, but certainly for gauge theories it has not. Like when you do the same thing for like continuum field theories, this has not been considered. We know that you will still get sensible entropies. Like for instance, you can compute the entanglement entropy that comes from a single superselection sector. That's sort of extremely weighting. You weight only one sector, and all of the other ones have weight 0. So you will still get some entropy. As I claim that this entropy will not have universal terms that match the central charges, or the standard nice things that you expect. But for all I know, there is a C theorem, and there's all the entire spiel can be redefined for in this particular case too. Just that no one has calculated anything about these things, and since we already have powerful ways of calculating things for this equally weighted situation, it's not clear that we will get much out of doing something fancier like this. But in principle, it's out there. And that will be one of my, things to do in the future. In fact, I have one particular hopeful application of this, which I will get to in the last slide. So let me wrap up. And this I already mentioned. This is the final non-trivial thing that I need to mention, which is that once you read everything I said can be repeated for non-abelian gauge theories too. The annoyingly non-trivial thing there is that it actually matters which representation you take for your gauge-invariant operators, because central elements that correspond to electric fluxes leaving the region will have these dangling indices because these operators are essentially matrices in the non-abelian gauge group. They will have these indices in the fundamental or whatever other representation the flux is in when it exits the region. You have to choose whether you include the entropy from these guys or not. Many people's intuition is that you should not include it, but it turns out that this is the kind of entropy you have to include if you want to get the if you want to run the analogous procedure for Chern-Simons and get the right topological entanglement entropy, which is 1/2 log k. That's a non-trivial thing to get. So you will have to treat the edge degrees of freedom as sort of physical. You cannot say that the entropy coming from them is just not interesting. At a much fancier level, which I will have nothing to say about today, this discussion, which is non-trivial already for SU2 gauge theories, is now being replayed for non-compact gauge groups with people working with SYK, right? I mean, people who are working with SL2R gauge groups are trying to understand how to get the entropy of black holes or things like that by properly summing over these sort of dangling indices. And the annoying thing is that these indices are sort of continuous for non-compact gauge groups. So it's a mess. Like we don't know how to get a well-defined entropy there. But everything I said here is like a baby example where we do understand how to deal with non-abelian degrees of freedom. But presumably in gravity, you also need to deal with these dangling indices of non-abelian theories to get the right kind of black hole entropy, where the Bekenstein-Hawking term is precisely the non-universal area term. So this will be interesting to see how it works out. But I profess complete ignorance on this subject. Really, I am not able to say anything meaningful about this. So let me conclude and release people if needed. And so the point is that the point that I try to convey is that as I said, even if I have constraints, then the fact that I have some underlying theory whose degrees of freedom have been constrained, like I did in a gauge theory, or like I did with fermions, this is important for getting the right entanglement entropy. You might find other measures of entanglement which don't care about this, but the entanglement entropy does care. And if we believe that entanglement entropy is, useful for understanding black holes or gravity in general or other things, then we need to take this seriously. An interesting thought is that we also don't know what are the Ryuta-Kanagi prescriptions for any of these other choices of boundary conditions. We don't even know what's the bulk dual of having Dirichlet boundary conditions at the entanglement edge. That would be really nice to. It would be really nice to sort of do this phenomenologically, if possible, to try to come up with different kinds of boundary terms that you can include on the entanglement surface in the bulk, and try to see if there is any kind of hopeful matching between how changing these boundary terms in the bulk changes the universal terms that one expects in the boundary. By doing this, you will actually end up writing a nice kind of dictionary, because then you will know which of these operators that you've removed from the boundary side to get some non-maximal algebra. You know which operator, like what this operator does in the bulk. It somehow induces this extra term on the boundary, on the Ryuta-Kanagi surface, or this extra kind of boundary condition. You sort of understand how that operator translates into the boundary in some specific way. That's very complicated, but it may be an interesting thing to try. And of course, in general, I do not know what, as I already mentioned to, I believe it was Michal, I don't know what these other entropies mean in terms of counting states, etc. But I'm pretty sure they have meanings. It's just that we haven't thought about them yet. So maybe things can be proven for them. Maybe they will give rise to more interesting C theorems, or easier to prove C theorems if we're lucky, or something like that. So I think it, and all of these different entropies and so on make sense already for scalar theories or 2D CFTs, minimal models, things like that. So there's no need to look at complicated, four-dimensional gauge theories to start thinking about these things. And with that, I would like to end, and thank you for giving me this virtual opportunity. Thank you.
Thanks, Djordje. Anybody have any more questions?
Of course.
Djordje?
Yes.
Can you hear me?
Yes, I can.
I just wanted to clarify one thing. So in the example you showed of the spin chain, it was very clear that there was a center.
Okay.
But is it a true statement that any non-maximal algebra has a center?
I believe it. Well, okay. Let me think. I think not. I think it's not true. I think Cassini had an example where he talks about this thing that he calls the balanced center. Well, which is kind of a misnomer, because the point is that there's no center. You choose an algebra such that you remove essentially all the electric field operators from the edge of your entangling region except for one in some particular way. And that kind of thing ends up giving you an algebra which has no center but is not maximal on your subregion. So no, in general that's not true, but it's a kind of relatively useful rule of thumb to have. That compared to what you normally expect, generically removing some operators in a nice way will give you a bigger center. But it's not always true. You can arrange special situations where that's not true.
Okay, thanks.
Yeah, I have a question. Like in the non-abelian cases that you considered,
yes.
Does something interesting happen if you take the limit in which the rank of the gauge group gets bigger? I'm asking this in the context of the discussion about holography, right? I'm trying to understand what happens in holography.
So at the level of the definitions, nothing interesting happens. The simplifying statement is that when the rank is very large, then the algebra simplifies because some operators are just suppressed by 1 over n. Non-abelian theories have complicated rules for how operators multiply, right? I mean, if you have a trace in one representation times trace in another representation of a Wilson loop, these will give you some complicated kind of OP-like thing where you're having to do, angular momentum addition, that kind of thing. So just the structure of the algebra becomes much simpler at large n, but that's essentially it. It does not affect any of the. It does not affect any of the. How should I say? Definitions I made.
So the statement of yours would be, and correct me if I'm wrong, that in the large limit, it's not that this boundary contributions would become subleading. I mean, that the universal terms from these non-trivial sectors would come as subleading contributions that would appear as, say, 1 over n corrections on the side.
Yeah, no, that I would not say that. In particular, if you have a weakly coupled theory, so which is essentially n squared or something like that gluons, like n squared photons, essentially n squared free photons. So you take your non-abelian theory to your UN non-abelian theory to be so weakly coupled, it's essentially just free photons. Then you will actually get non-trivial universal terms which are proportional to n squared. So so even at the very leading order in n, and you will generically get some important universal terms that come from summing over all the sectors that you cannot get from just one sector on its own. So yeah, I think so. You kind of have to keep track of everything. There's no simplification I know of. Some certain calculations get simplified, but there's no general nice miraculous statement I can give you at the level of algebras about how this works.
Thank you.
Mm-hmm.
So let's thank Djordje again.
Hey. I can't. Oh, there it is. Okay.